So that makes sense. All right, scoot it back.
Okay, I'm on the very edge.
Okay, if you don't balance, then someone needs to move.
Oh, it's
It
fine.
works!
Okay. That's like 16 inches, and that it's like 17. It's 18 inches. 18 inches. Okay. I'll process that.
Okay.
Yeah.
All right.
Are you recording?
Yeah.
You're recording right now?
Mm-hmm.
Okay. Okay. That's like 14 inches, and that's like 20 inches.
20?
Yeah. When do you want to start?
Okay.
Ready? Okay, jump in. Are you pressing left? No.
Wait,
You
what
can
are we?
record 5 and then divide it by 5.
Yeah.
Press left every time.
Huh?
Ready? Ready?
Okay, last
Okay.
leg.
Okay, let's start now.
1,
No, that's not. No, great.
Wait, does it have to go back and forward? Is that
back
one?
and forward.
Okay,
Oh.
11.5. Yeah,
I'll look.
good. Okay, ready? I'm gonna start it next one.
Yeah, Shivam, you're kind of in the way.
Okay. Okay. 3, 2, 1.
One, two, three. Yeah.
Okay.
Am I watching it?
Yeah.
Oh shit.
One, two.
Oh.
That looked like a good one. Let's go.
Okay, go.
Okay, is that one spin? Okay. Oh my god.
Alright. Yeah, I got the pen.
Okay. You ready? Everyone ready?
Yeah, I'm ready.
Yes.
I'll start timing once you guys stop spinning. Ready? Okay, stop spinning.
Stop. Okay, stay there for 1 round.
Stay.
Okay, and
Okay,
now
start
we're
walking in. Walk in.
Stay there.
Okay. That's exactly what we're supposed to know. We gotta figure out. Did it change speed?
There wasn't any noticeable change.
Yeah, that's what I expected. It shouldn't change much. No. Okay, yeah. I'm ready.
Okay.
Oh. Fastest.
Ready? Okay, stop spinning.
I mean, it's also unfair.
And
Okay, start moving. Yep, that's exactly what we're supposed to do.
Slow down because you guys are pushing it, so I think it's probably the same.
It's slowing down because
Yeah, I
it's
don't
pushing
think
your
you're gonna be able to notice any difference. Okay. For the seesaw experiment, the question was, what effect did the changes you made to balance the two group members have on the torques they exert on the teeter-totter? To balance a lighter and heavier person, the lighter person would have to be farther from the center of rotation than the heavier person. Torque is the force which causes a change in rotation. It is a force applied at some distance from the center of rotation. Moving a person further increases the torque, while moving a person closer decreases the torque.
The second part of a question asks, what can you say about the sum of the torques exerted by two group members on the teeter-totter? We could say that the sum of these two torques was 0 because all forces were balanced.
For the swing experiment, the first question asks, which of the characteristics above, when varied, had the greatest effect on the period of swinging? The length of the swing had the most effect. The formula for torque, which is torque equals distance from center of rotation times force, states that a change in distance will affect the amount of torque exerted. The starting height of the person had the second greatest effect.
the second question for this experiment is it relatively easy for the two swingers to synchronize, and why? It was easy for the two swingers to synchronize if they started at the same height because mass does not affect the period of the pendulum and the length of the swing was the same?
So for the merry-go-round experiment, the first question says, what would happen if your feet slipped while you were spinning around? Would you fly off away from the center of the merry-go-round? Would you continue in a straight line? Or would you fall towards the center? And the answer we proposed was, if I slipped, I would fall straight in a straight line tangent to the circle away from the center of the merry-go-round.
The next question for this experiment is to describe below the path the ball took when released from the viewpoint of the rider and the observer. The outside observer noticed that when we dropped the ball would fly straight in a tangent line every time. The rider observed the ball accelerating away from them.
So the third question for this part of the experiment said, from the perspective of the merry-go-round, what are all the forces acting on the ball as the merry-go-round turns? From the perspective of the observer on the ground, what are the forces on the ball? And after the ball is dropped, which observer's forces are useful in describing the ball's motion? The rider noticed that torque was acting on the ball. However, from the perspective of the observer, a centripetal force was acting on the ball. After the ball is dropped, gravity and angular momentum can be used to describe the ball's motion.
For part 2 of the merry-go-round experiment, the question is, what happened to the period of revolution when the person walked towards the center? The period of the revolution decreased because the time it took for the merry-go-round to complete one revolution decreased.
The second question asks, did the speed decrease, stay the same, or increase? How did you know this? We said that the speed increased. This is because the period of revolution decreased. Therefore, the merry-go-round took a smaller amount of time to travel 2 pi radians, or 1 complete revolution, so the angular velocity is greater.
The next question, what must happen to the person's speed then if angular momentum is to be conserved? Did you observe this? According to the equation for angular momentum, which is angular momentum equals moment of inertia times angular velocity, the distance from the center and the angular velocity are inversely proportional. So if momentum is conserved and the distance from the center is decreased, then the velocity of the person increases.
Alright, that's happening again, so. Oh,
Okay, toss it. Nice catch, right?
Yeah. Oh my gosh, man.
wait, what happened?